Hello, everyone. Welcome to another wonderful day of chemistry. So today we're going to be taking a look at how we can try and control the rates of a reaction by looking more at the molecular level. So one of the important things to keep in mind when we're talking about chemical reactions is really what we're doing is talking about molecules moving in between two stable states that we call the reactants and the products. However, since we know that a system is stable as reactants and stable as products, it means you have to go between the two, you have to go through some no man's land where nobody wants to be. So we call this region the transition state. So we can go ahead and examine this if we look at the very favorable reaction of combining nitrous oxide with nitrogen oxide to form N2 and nitrogen dioxide. So a lot of N's and O's here. But one of the important things to do is take a look at what happens on a molecular level. So nitrous oxide is kind of unstable because we have a nitrogen with a positive charge over here. It's got 4 bonds in it, don't like it. And we have an oxygen here with a negative charge. It minds that a little bit less. But this still isn't necessarily a very favorable species. And we have nitrogen oxide over here with a radical charge. So in order to try and figure out what happens, we take a look at our reaction and say, oh, an oxygen has to move from this nitrogen to this nitrogen. Well, how can we go ahead and do that? Well, simply, we're going to have to slowly break that oxygen bond and form an oxygen-nitrogen bond here. However, the oxygen atom doesn't spontaneously jump from one nitrogen to another. It has to actually lengthen this bond while shortening this one simultaneously to generate a product. And while this species is very favorable, this guy isn't so much. And it's going to have an associated energy with it. And this is called the activation energy. And the point at which this activation energy has maximized, the most difficult point to reach, is called the transition state. And so a good way to think about this transition state is if I'm going on a path from my reactants to the products. Well, there's a whole bunch of places that ways I could go from here to here that are very unfavorable. But there's going to be one way I can get from here to here that's the easiest way. So this is often called the mountain pass analogy. We're looking for the lowest way through these mountains to get from reactants to products. And in this case, it's going to correspond with just the right lengthening of this nitrogen-oxygen bond accompanied with just the right shortening of this bond. And they have to go very much in sync. And this is often a little bit difficult as we're trying to change both of these distances concurrently. We're trying to shorten or lengthen this bond, which again, you'll notice is very hard. And you're probably not going to be able to lengthen this nitrogen-oxygen bond at all until you've shortened this nitrogen-oxygen bond at least a bit. So we have to find the exact right way to get through here. There's lots of ways to go from reactants to products that would be very unfavorable, but again, one most favorable transition state. And it turns out one of the reasons why we care so much about this transition state and its activation energy is that it's really what's going to control the rate of the reaction. Because in order to go from here to here, I have to get up here before I can get to the other side. And in general, what we're going to find is the higher the activation energy, the slower the reaction. Well, and that makes a certain amount of sense. But how do I find the energy to get over this unfavorable barrier? Well, it turns out molecules always have some energy inbuilt into them. And it tends to reside as temperature. Because remember, way back to kinetic gases, temperature is another metric of the kinetic energy of a gas. The higher the temperature, the more energy a molecule has. And so what it can do is say, if I have this amount of kinetic energy, where this is my activation energy, I am a certain percent likely to get from here to here. And so as the system heats up, its average energy increases, but more importantly, the percentage of energy that's above a given threshold goes way up. And we can go ahead and figure out, using temperature and our activation energy, the exact likelihood that a molecule will undergo a chemical reaction. We can do this using what's called the Arrhenius equation. And this relates our good old friend, the rate constant, to what's called the Arrhenius constant and the exponential of the negative activation energy over our ideal gas constant and the temperature. And what we tend to see here is that as the activation energy gets bigger and bigger, so that barrier goes up and up and up, we have a larger negative exponential, which means that this number gets very small. And temperature is a way to essentially modulate that. As the temperature gets higher and higher, we have more energy to effectively make this exponential smaller or more likely to go from A to B. And so again, this rate constant is really going to be related to this likelihood of jumping from our reactant state to that transition state. And we're assuming once we get there, it'll be favorable enough to just go downhill to generate products. Now, one of the big things that is actually fairly useful to keep in mind about this rate constant is that we tend to find that when you raise the temperature by about 10 degrees Kelvin, due to the magic of logs, it tends to double the rate constant. And again, the exact relationship will be dependent upon what your exact activation energy is. But this really shows how much we can speed up a reaction by increasing the temperature. 10 degrees Celsius, which is about more than 20 degrees Fahrenheit, is more than enough to double the rate of a reaction. So if you want something to go, you make it hot. However, we also have a dependence upon this Arrhenius constant. So let's go ahead and talk about that for a quick second. So Arrhenius constant is going to be controlled by several key factors. And the first of which is no surprise. It's going to be the order of the reaction, because you'll note there should be no units on this exponential term. We have energy divided by energy. So exponentials never really offer anything to units. So not too surprisingly, if I've got a 0th order reaction, my Arrhenius constant is going to have units of moles per second or minute. If I'm talking about a 1st order reaction, it should just be per second. And if I have a 2nd order reaction, it should be per mole per second. And so we'll see a big difference just in those form of units. But also related to this is the number of ways our reactants can collide, because not every single collision of our two reactants can generate a product, because it turns out you need to have everybody lined up. In order to transfer an oxygen from one nitrogen to the other, I have to make sure that that oxygen is hitting the nitrogen. If it hits the oxygen, I don't have anything. If my two nitrogens collide, I also don't have anything. And so this is going to reduce the likelihood of going from reactants to products, as if something doesn't matter how the two molecules hit, my reaction rate should go way up. And related to this, there's a lot of different effects of entropy. And this includes the fact that when we're looking at this potential energy profile, we are just looking at potential energy or enthalpy. We aren't including free energy. So if there's a lot of different ways to rearrange your reactants or products, this can make them a lot more stable and less likely to pass that transition state. As well as, again, it's not just the energy of the transition state, but its breadth. But we won't really go into all these details, but it's important to note there are other effects that mostly can be categorized as entropy that make a difference. But most importantly, what we tend to see is that every reaction will have its own Arrhenius constant. I can't take the Arrhenius constant from one reaction and apply it to a different one. But once I know the Arrhenius constant for a given reaction, it will stay relatively constant as I go from one specific species to another. However, this means that if I'm trying to model the kinetics of a reaction, especially with respect to temperature, I need to go ahead and find out the Arrhenius constant and the activation energy for that specific reaction. And one of the ways we can do this is take our Arrhenius constant and try and evaluate how that rate constant changes with temperature. So in order to do that, the first thing we're going to want to do is make it so it's easier to fit this equation to a straight line. So I have to get rid of that exponential. So if I take the natural log of both sides, I can go ahead and pull out that Arrhenius constant as a natural log of A. And all I'm left with for the exponent is just minus activation energy over RT. Now this looks a little bit better, but remember that temperature is going to be our X variable. So I'm going to want to go ahead and pull that out here. Natural log of K would then be our y variable. So then from this, we've got a very natural linear equation where natural log of k is our y, 1 over t is our x. And this means that negative activation energy over r's will be my slope, and the natural log of the Arrhenius constant will be my intercept. And so by graphing our natural log of our rate constant versus inverse temperature, we should be able to generate a nice straight line. And again, the slope should be the negative of the activation energy over r, and our intercept would then be related to the Arrhenius constant. So by a simple linear fit, after having performed several determinations of rate constants, you can figure out a lot about the temperature dependence of a given reaction. So next time we're going to zoom out a little bit and try and figure out how we can control the rates of the reaction by varying a lot of different properties. Until then, take care.